between the spatial object and between the algebraic representation of an object. So this is the first time we're able to connect those really explicitly. As you go on and you're doing more with the graphs and area under graphs, you'll do that even more. But it kind of starts with just knowing how the first derivative and the second derivative can help you define a graph. So from an algebraic representation of an equation, how you can get from that to knowing what the graph looks like without having to graph it. Cool? Do you guys all have your graphing kit? Let me grab one.
Yeah.
Because we're going to test some stuff later on. But the idea is we should really only be using the graphing calculators in this unit to test what we're able to find mathematically. Okay? So we're going to start, and I want to look just to kind of give you a sense of what this is going to allow us to do. So here could be a graph, kind of a piecewise function that you might find in calculus. So as we look at this graph, there are all different elements of the graph that help us understand it. So the first is, like, if you look here, you're starting here. This is going to be an absolute minimum of the graph, right? So that's one way that we describe the graph. What's here? Anybody know yet?
I don't know, I think that's not an extreme value, but it's the derivative of 0.
Excellent. It's not an extreme value. The derivative is 0. It's called an inflection point. So when you have the derivative equal to 0, but it's not a maximum or minimum, and we're going to be able to take Spencer's definition and define that more mathematically. So the mathematical definition of the inflection point is going to be that it's where the first derivative is equal to 0, but the second derivative does not have a sign change. So we're going to be able to solve for that without just looking at it. We're going to be able to solve for it mathematically. How about here? What can you already tell me about this point? It's max. What kind of max?
Absolute.
Absolute. So how does that relate to what we know about derivatives?
It's gonna be the derivative 0, and then it's gonna have the sign change.
Ah, good. So Spencer already extrapolated what we said over here. So because this is an actual maximum, we are going to have a sign change at the second derivative. All right, this point, Michael, what can you tell me?
It's a local min.
Good. Why local instead of absolute?
Because it's not the lowest point on the graph.
Excellent. What can you tell me about the derivative, Michael?
It's 0.
Excellent. This point.
Wait,
Shikai, what can you tell me about that?
Is that undefined?
Maybe, so let's talk about this, and maybe
no.
just because of this point up here?
No, the local min.
Maybe, just because of the way I drew it. Let's talk about this, which is, I think, what you're pointing to here. Why were you wondering if that was undefined?
Because it's a cusp, or is it
A cusp.
a corner
Yes.
or cusp? So
It's a straight line.
So that's the one I intended to draw exactly as a cusp. But you're right, Shikai, that could potentially be just because of my bad drawing. But so, what do we know then about a cusp? Shikai, what do you know about that then?
No. The local mean, when the graph is the local mean, I'm saying the local mean is a cusp.
Yes, I'm saying potentially yes, I agree with you. I didn't intend to draw it like that, I didn't mean to, but you're right, it could be.
Can
Let me
local max
flatten
be
it out.
cusp? Oh, because it has the...
What makes something a cusp?
You have two straight lines.
Well, just the derivatives undefined at the point.
Right. So the derivative is undefined at the point. So here we have, so let's say potentially that I drew this better. Ah! Okay, is that better, Shikai? So it looks more parabolic there. So that's a local min.
Yes.
This is a cusp. Right, so we're going to learn also today mathematically how we can determine a cusp. So at this point where the derivative is
0.
Undefined.
it's undefined at the point.
Cusp is when graph is like this. When when this reaching the maximum is 0, when you reach the minimum is undefined.
Well, a cusp could be either way though.
Then how do you
A
know
cusp,
which one is
so
undefined?
Shukai, a cusp can be at a maximum point, or it could be at a minimum point.
It's like
Both of those are cusps.
So
corners just like straight line, cusp is curved line.
Right, because we can't make the tangent at those points. Both of those are cusps.
oh, that's right. Yes.
Okay?
Okay.
So the definition of a cusp is that the derivative
is
is undefined at that point. Not that the function is undefined, that the derivative is undefined at that point.
Okay.
Okay?
Yep.
So, but we're gonna see then how that works, how we can know that something is a cusp using the first derivative and the second derivative. So we'll be able to tell that something is a cusp rather than a local min or max because the derivative is undefined, but the behavior of the second derivative is still consistent with a maximum. So that'll help us understand some of these things. So this is kind of what we'll be able to tell using the first derivative and the second derivative. This is one of the most important ways that it's useful. And once you know how to do this, you'll forget all other ways you knew how to graph. So all the other ways you learned in Algebra 2, you'll forget because this is going to be way easier. So that's a good thing. Cool, any questions about this so far? All right, so the first derivative test. So if the derivative changes sign from positive to negative at C, then f of x has a local maximum value at C. So what that would look like, so let's say we have this graph and we have this local or global maximum, it doesn't matter. All global maximums are also local maximums. So we have this local maximum. So given this function, we will be able to tell from the derivative. So the derivative of this whole section is going to be positive. The derivative of this whole section is going to be negative. So that's going to tell us that it's a local maximum. So, and then the same thing is going to be true at a cusp. So even though this is a point at which it is undefined, the derivative, still here the derivative is going to be positive, and here the derivative is going to be negative. Then the opposite thing is going to be true for mins, whether they're actual mins or whether they're cusps that look like mins, which is what Shukai was pointing us to, right? So the opposite or the converse is true here. So if you have this local min, the derivative is going to be negative and then positive. So we know something is a max if the derivative goes from positive to negative. We know it's a min if it goes from negative to positive. And you're going to start going like this. The derivative goes down, the derivative goes up. That's a min. The derivative goes up, the derivative goes down. That's a max. Same thing for a cusp. So a cusp acts like Shukai said, it acts like a minimum when the derivative here is negative, and then after the undefined point, the derivative is positive. Okay? Everybody okay with that so far?
Yeah.
So let's see some actual examples of that. Or we gotta do one more part of the definition and then we'll come back and revisit. Okay? So essentially what you've been able to do since Algebra 2 using factoring is to find the extreme points, right? You've been able to factor, you get x equals 2, x equals negative 2. Now using the derivative, you can tell if that x equals 2 is actually a max or a min. You can tell if that x equals negative 2 is a max or a min. Cool? Okay. So if the derivative does not change sign at C, then f has no local extrema at C. So Spencer, what would that point be where it is not a max or a min, but the derivative is 0?
Point of inflection.
That's our point of inflection. So now we know something is a point of inflection if the derivative is 0, but the sign doesn't change. So in this case, the derivative would be positive, and then the derivative after the point of inflection would still be positive. Anyone want to take a chance, come up and see if they can draw on our graph what it would look like if we had a point of inflection where the derivative was negative then negative? So this is a point of inflection where the derivative is positive from the left and positive to the right. What would a point of inflection look like if it was negative from the left and negative from the right? Good. So that would give you a point of inflection where, forget Spencer's little parabolic thing right there, but from here, the derivative is negative. At the point of inflection, the derivative is 0, and then afterwards, the derivative is still negative. So if the derivative changes sign, it's a max or min. If it stays the same, it's a point of inflection.
So at that point, the derivative is still 0, right?
Yes. Because we have that horizontal. Okay. And then let's go down a little bit so you can get all this. So blah, 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 fancy language, copying your notes. So basically the last part of that describes if you have a bounded function. So if you have a bounded function where it's not infinite to the left or right, just defining from where it does come, whether that makes it a local min or a local max. Which is, we know, much more common in calculus than the functions you're going to see in algebra 2, because with calculus we're talking about real things. We're talking about things that have beginning and end. We're talking about things that exist in space, right? When we start revolving functions to create disks and washers and cups and pyramids, they're real things, so they have a beginning and an end. So this becomes important when we talk in calculus versus in algebra 2. All right, drop your pen dramatically when you're done so I know you're ready. So far the Oscar goes to Michael. Poor Shukai, he's got to think in another language and then write in English and try to keep up with.
Not really.
You're good?
I have to write in good handwriting so I can give it to other people.
Okay, which takes the longest in any language,
Yeah.
right?
Oh god.
All right.
I think I'm good.
Okay, great. All right, so let's look at how this works with an actual function. So we're going to use the first derivative here to figure out our points of extrema and whether they are points of inflection, local mins, or local maxes. So I'm going to do this first one completely as an example, and then I'm going to try to give you one similar to do on your own. Okay? So listen carefully, hold your questions till the end, and then I'll take your questions after I do the full model if I haven't already explained it. Cool?
Yep.
All right, so for the first derivative,